Hello students, once again you are welcome to Waidsum Academy. Today we're looking at Physics IGCSE, Cambridge Physics IGCSE May June 2018, paper 4-1. Today this is the part 2, and in part 2 we are looking at questions starting from question 5. You can check out our part 1 from question 1 to question 4, and part 2 today we're looking at question starting from question 5. Then the first question here is a ray of light in air is incident on a glass block. Now the light changes direction. State the name of this effect. So when a ray of light is incident to a glass block, let's say for example if you have a glass block such as this, quickly let's take a look at this. If this is a glass block, and any ray of light that is incident to it can either be reflected, let's say this is normal, broken lines. Any ray of light that is incident to it can either be reflected. Let's say a ray of light is coming like this. It can either be reflected, meaning it goes this way. If it's coming like this, it can either be reflected or refracted. But most likely refracted. Refracted is like this, meaning it goes inside the glass, but it's bent. Okay, it will not come in the same way it was coming before. Like it will come like this. No, it was supposed to be coming. The ray of light was supposed to be going this way. But it will go like that because now it has met an optically denser medium, so it's bent. So it becomes bent, okay, towards the normal. Becomes bent towards the normal. This is the normal line. So it's either refracted or it's reflected. Reflected is this way, meaning the ray did not even go into the glass. Okay, it just hit the boundary and changes direction. Okay, if it hits the boundary and changes direction, it didn't go into the glass, that's reflection. So the top one is reflection. For this top one is reflection. So the answer we could provide here is, but most likely, since there are two media, as the case may be, it's better we go for refraction, because when a ray of light that is coming from air hits glass, it's certainly going to refract. So we talk about refraction. Okay, so we say refraction. But some other students can choose reflection. Still they are correct. Why? Because the two phenomena can happen. Any of these phenomena can happen. Or sometimes both of them can happen same time. Maybe some of the ray is refracted, some are reflected. So either we write refraction or we write reflection. Okay? Either we write refraction or we write reflection for this question, or reflection. Okay, so that's the solution to this question, refraction or reflection. But refraction most likely, because a ray that's coming through the air hits the boundary, reflection hits the boundary between air and glass, is certainly going to refract and passes through the glass. It's certainly going to refract and passes through the glass. The air is optically less dense, while the glass is optically denser. So that's why when the ray enters the glass, it bends towards the normal. You see the angle. Look at the angle of incidence. You know the angle of incidence between the ray and the normal. The angle of incidence was a way big, maybe 60 something degree. Now it's like 20 something degree. Okay, the refracted ray is like 20 something degree. The refracted ray is like 20 something degree. Okay, the incident ray or the incident angle was bigger. Why? Because you've moved from a less dense medium, which is air, to a denser medium, which is glass. So we say that the ray is certainly going to refract through the glass and is going to bend towards the normal. Okay, so that's the first approach to the first question. Now let's see the next question. It says, the second one is the cause of the effect. What's the cause of the effect? What causes the refraction or the reflection? What causes it? What causes refraction? If it's refraction for one Roman figure 2, if we chose the refraction, it means the change of medium. You can say change of medium, B, or change of speed. We can say change of medium or change of speed. So here we can simply say change of medium. If we chose the refraction, so our response will be change of medium, because you've changed from air to glass. You've changed from air to glass. You've changed from air to glass, change of medium or change of speed. Certainly when you change from air to glass, the speed will change. The speed will change. It will slow down. The speed is lesser in glass compared to when it was in air, when the ray of light was in air, because of refractive index. Okay. We can also say because of refractive index as the reason for refraction. Change of speed or change of medium. So this could be the solution to this one if you're choosing this. If you're talking about reflection, what could be our reason? What could be our reason why we choose reflection if we decide to choose reflection? Okay. If you're choosing reflection, we mention the surface or the boundary. Here is the boundary, meaning the ray hits the boundary between the air and the glass, and then it bounces off. It didn't go through it. You measure the boundary. So if you are talking in terms of reflection, you measure this boundary. So when the ray of light hit the boundary, instead of penetrating through it, and it's turned back, it's reflected to another side. So it didn't go much through it. So you can say, for this one, you can say because of the surface. Say the surface of the boundary. If the surface is very smooth, then there will be a nice reflection. If the surface is rough, there will be dispersed or diffuse reflection. Okay, so we say due to surface. Reflection is due to the surface that the light hits. If the light hits a good surface, it's reflected. If it hits a glass, it's able to penetrate. There are some surface, the light will hit, it will penetrate through it. There are some surface, when it hits them, it cannot penetrate. Is that okay? Now we go to the next question. It says figure 5.1. Figure 5.1, drawn to a full scale, shows a thin converging lens of focal length 3.5 or focal length 3.5 centimeters. So meaning the focal point will be 3.5. Here we're going to count. Look at the define both the horizontal and vertical. 5 tiny boxes represent 1 centimeter. 5 tiny, 1, 2, 3, 4, 5. So 5 tiny boxes for the horizontal is 1 centimeter, and also on the vertical is 1 centimeter. So we're going to count 5 boxes to locate our focal point. Okay, because it's a 3.5 centimeter. So you got to count 3.5 centimeter away from this optical center. From this optical center, we count 3.5 centimeter. So 1 centimeter is 5 tiny boxes. 1, 2, 3, 4, 5. So here, to this point is 1 centimeter. To this point is 2 centimeter. To this point is 3 centimeter. And then 3.5 will be 2.5 boxes away. 1, 2, 3, somewhere here. So here is where we're going to put our focal point. Here is where we're going to put our focal point, this place. Okay, F. You count also to the right side. 1, 2, 3, 3.5 is here. You put F here also. So we put it F here and we put it F here. Okay, we put it F here, and we also put it F here. So those will be your F, your focal point, okay, which are 3.5 centimeter away. So what we can do in this case we just sketch because we're not writing on the exam paper. So we use just our board. So if this is our optical lens, if this is our lens, the optical center is here. Let's draw our vertical line so we can ascertain our optical center. Okay, so let's have our principal axis. The principal axis is this horizontal line. This is the principal axis. Okay, let's assume here to here is 1 centimeter, 2 centimeter, 3 centimeter, 3.5 is here. So let's say here is our F on this side, our principal focus, or our focal point. You count also this way, 1, 2, 3, 3.5 is here, our focal point. Okay, now an object is 2f away, more than 2f away. Let's see from the question paper. The object, if here is 1, 2, 3, 3.5 is here, right? Another half, 1, 2, 3. So it's even more than, this object is beyond 2f, is beyond 2f. So similarly here we should have something like that. So beyond our 2f, the object will be beyond the 2f. Okay, the object will be beyond 2f. This is 1, 2, 3. So the object is here, super far away. Okay, but in this case, let's just put it just here, because it's not too far from the lens. Okay, we say the object is here. Okay, the lens, we can make it more. Okay, let's say this is our lens. There's no longer stopping here because of the height of this object. Okay, so this is our lens. It is not too accurate. It's just, don't mind our drawing. It's just a sketch. Okay, this is our lens. Okay. Now 2f on this. Here is 2f. This place 2f. And the object is beyond 2f. Now on this other side, our 2f is here. One, two, three. Our 2f is here. Okay, now let's see what the question wants us to do. Okay, I reduce the size so that we can do it one shot. Now let's see what the question wants us to do. What the question wants from us. Okay, here it says on figure 5.1, mark each of the two principal focus. Mark each of the two principal focuses and label each with letter F. We've done that. Okay, we've marked, we've counted. This is the principal focus on the left side and the principal focus on the right side of the lens. So we've done that. We've even gone beyond what they've asked us. We've labeled 2F. Okay, so that's the first one. We get the marks, the corresponding marks. This is one mark for being able to locate F. An object O of height 4.4 centimeter is placed in a distance of 7.5 centimeter from the lens. You remember 2F is 7 centimeter because 1F is 3.5 centimeter away from the lens. So 2F is 7 centimeter. So the object is beyond 2F, 7.5 centimeter away from the lens. Now on figure 5.1, draw the rays from the top Draw the rays from the top of the object to locate the image, and draw and label the image. So determine the height of the image. Determine the height of the image. The height of the image, we can just, after we finish, we can count using this one. 5 tiny boxes to be 1 centimeter. We can just count without calculation. Okay, what we need to do first is to quickly draw our image. To draw our image. And to do that is to the ray of light coming from the object, the ray of light coming from the object, you know, every object has a light coming from it. So the ray of light coming from the object moves parallel to the principal axis, okay, moves parallel to the principal axis. See, it moves parallel to the principal axis. This ray is parallel to the principal axis. Remember, the principal axis, this horizontal line is the principal axis. So they are parallel. These two lines are parallel. When it hits this lens at this point, it will refract. It will refract to pass through where? Through the principal focus. To refract to pass through the principal focus. Okay, everything here is not accurate because we're not using graph paper. Okay, so it will refract to pass through the principal focus. Then another ray of light that's coming from here and passing through the optical center another ray of light, okay, it's straight, okay, don't mind our error or mistakes, that is passing through the optical center will remain undeviated. See, they meet here, okay, it remains undeviated. See, where they meet, that's where the image is formed, this point. So we form our image by drawing an arrow downward. The image is inverted. The image is inverted. The object was standing upright. Look at the object. Here is O, object. The object was standing upright. The image is inverted. It's turned upside down. Okay, the image is a real image. It's a real image because it can be formed on the screen. It can be formed on this screen. Okay, the image can be formed on a screen, so it's a real image. Now, this is what they want us to draw. So I haven't drawn this. Then you go to secure your 3 marks. Okay, you go to secure, draw and label the image. We've drawn it, we put I, we've labeled it. Determine the height of the image. Okay, the height of the image, like I said, we just use we count 1 centimeter, right? So in this regard, we just see what we have. 1, for this one vertical, 2, 3. I think something, you know, we didn't measure this. If this is 4, this would be like, sorry, if this is, yes, 4.4. You know, this one was 4.4. If this is defined as 4.4, was given to us, the height of the object as 4.4. This could be, this is a little bit less, maybe 4.1 or 4.0. Okay, this would be 4.1 centimeter or 4.0. You can measure and determine that. Is that okay? So we say the height of the image is 4.1 centimeter. Could ask question B, Roman figure 2. No, Roman figure 3. So we say this is B, Roman figure 3. We say 4.1 centimeter. Okay, they will give you a range. The examiners will give you range. Maybe they will say from 3 point something to 4 point something. Okay, we can say 4.1 centimeter, the height of the image. Okay, we go to the next question. State and explain whether the image is real or virtual. The image, we already, during the course of explanation, we already mentioned this. Was it C? Let's see, question C or, okay, B, Roman figure 4. B, Roman figure 4. B, Roman figure 4. B, Roman figure 4. My board has a Yankee. Yeah, I hope we can. Is it state whether the image is real or virtual? It's real. A virtual image is not a real image, right? And it cannot be formed on a screen. This is a real image. Why? You also have to give the reason, because you can just say because it can be formed on the screen. It can be formed on a screen or projected on a screen. On a screen. Because it can be formed on a screen. Okay, so that could be the reason, and you get it's just 1 mark. We don't need to waste a lot of time. Now it's a figure 6.1 shows wavefront approaching a gap in a barrier. Figure 6.1 shows a wavefront approaching a gap in a barrier. Okay, you say on figure 6.1, draw 3 wavefronts to the right of the barrier. Okay, so this one, we have a barrier. Question 6. Okay, this is a different question now. Question 6a. So we have a barrier. We have a barrier with a small narrow gap. Okay, so we have wavefront, 3 wavefront approaching this barrier. So when a ray of light gets to this place, what happens? They will be diffracted like this. They will be diffracted like this. And the wave will move in this manner. Okay, so like this. So you do this, you get your marks, whatever number of marks that this question carries. Now let's move to the next question as fast as we can. Is it on figure, draw 3 wavefronts to the right of the barrier. We've done that. The 3 to the right of the barrier, we've done that. On figure 6.2 shows, figure 6.2 shows the gap in the barrier increased to 5 times the gap in figure 6.1. See, do you see the gap? The gap in the barrier has been widened 5 times the gap in the previous barrier. Now, on figure 6.2, draw 3 wavefronts to the right of the barrier. Now, if the gap widens, then the diffraction becomes very small. The diffraction becomes very small. If the gap widens, the diffraction becomes very small. Now we've increased the gap almost like 5 times. So the diffraction becomes super small as this. Now these are the wavefronts. 3 wavefront approaching this barrier. Okay. So what we have something like this. we'll have something like this. Okay, and the diffraction is not intense as the one we've seen. The diffraction is very little. Diffraction is very little, okay? Not as intense as the one we've seen before. See? As if they didn't really diffract much. So this is what happens because they have a lot of gap. They can just like as if they just went through the gap. The ray of light or the wave that is coming or the wavefront, as if they just went through this gap and there's nothing serious as such. So this is what we need to show. You can see the difference between this and this. Okay, this one with small gap, there's a lot of diffraction happening here. This process is diffraction. Okay, when a wavefront passes through, meets a barrier in front of it, the wave will diffract. Okay, it happens to water wave and light wave. When they meet any barrier, all kinds of wave, okay, when they meet a barrier and there's a gap between the barrier, they diffract. When a wave passes through a barrier, it diffracts. Now, how much the differential you have depends on the gap. If the gap is very small, they diffract a lot. They diffract more. But if the gap is wide, then they don't diffract much. They just pass through, only few are diffracted, and then it's not as intense as a narrow gap. Okay, so that's that for this question. Let's move on to the next question. Is it described with the aid of a diagram and experiment using water waves with, that shows the reflections of water wave that occur at a straight barrier. Okay, if there's a straight barrier, if you have a water wave, let's say we have water wave, I think we can take this one B, right? This is 6B, and this one is like an experiment. So this one, I think it will attract more marks. You can get up to 4, 5, or even 6 marks for this type of question. So you can describe the experiment, you can give an aim of experiment to show the reflection in the water wave. Aim, you can say, to demonstrate reflection in water wave. Okay? Demonstrate. So I'm not going to write everything. To demonstrate reflection in water wave. Reflection in water wave. In water wave. Okay, let's look at the question again. Say, describe with a label diagram an experiment using water waves that shows the reflection of waterfront that occurs as straight barrier. Okay, straight barrier, no gap. I think this one no gap. So, because if there is no gap, that's when you have reflection. If there is gap, there will be diffraction. If there is gap, there will be what? Diffraction. If no gap, it's a straight barrier, then we will have so let's assume we are using wavefront. Okay, we can use wavefront. Okay, here aim, apparatus, what are the things you need? You can mention them. Apparatus, the things you're going to use. You can mention them. But I want to jump to the procedure. What do you need to do? Okay. Apparatus, what are the things we need? We need water, we need a can or beaker, whatever. We need water bath, or wavefront. We need wavefront. Need wavefront. You need a barrier, a straight barrier. Without a barrier, it's a straight barrier without a gap. Okay, straight barrier. A straight barrier, something that can provide reflection. Okay, straight barrier without, so that in this case, we will not be talking about diffraction. We will not be talking about the diffraction. A straight barrier can use anything that can reflect the water. Okay, straight barrier, whatever you need, then procedure, you measure whatever you need. It's not only limited to this, okay? You can think of anything you need for this type of experiment. Now, procedure, here, I will just show you diagrammatically, okay? No too much writing. So here, let's use the water, let's use wavefront to represent the water. Let's use wavefront to represent the water. And then there's a straight barrier here. There's a straight barrier. There's a straight barrier here. Okay. Okay. This one I want to change this wavefront. Okay. I want to change the direction of this wavefront. Okay, I want the wavefront to be like this. That's why in the exam it's better for anything drawing, use pencil. Anything drawing, plotting, use pencil, don't use pen. Because in drawing, you can make a mistake and you can easily erase your mistake. Yeah, we're using the water wave like this. Okay, now the water wave is traveling like this. Let's say the wave is coming like this. So it's incident to the barrier. When it's incident to the barrier, the wave will be reflected. The wave will be reflected. The wave will be reflected like this. Okay, we're going to extend the barrier a little bit. The wave will be reflected. The wave will be reflected. So this will happen. Here we have the normal. First, let's signify the normal. Here's the normal line. With broken lines. So what happens when this one comes here? When it hits the boundary, this barrier, when the wave hits this boundary, this barrier, what happens? It's reflected like this. You must show with arrow the direction, meaning it bounces off. So this is what you need to just sketch for procedure and diagram. You get in your explanation, you can say area of light is incident to a straight barrier, and when it hits the barrier, the wavefront begin to move back in the same medium. Begin to move back in the same medium in a reflected manner. So you can just, and there you describe the angle of incidence of the wave equal to the angle of reflection. The angle of incidence equal to the angle of reflection. So you write all of this point, and you say I, angle of incidence, angle I is equal to angle R. is equal to angle R. So all of this you write down. You measure this barrier, could be any plane surface, and then you measure the wavefront as they hit the barrier and they reflected to move in the same medium. Why I say medium? Because it's both air. Let's say the medium is air, so it's moving in the same medium. It's not changing media. It's not changing from one medium to another medium. Hence, it's moving in the same medium. Okay, it didn't cross over to the other side. It didn't enter into a glass or into water, or into another surface. So it's moving on the same medium. So hence, it's moving on the same distance. So this is what you need to just sketch for this experiment. In conclusion, you write that the angle of incidence equal to the angle of reflection, and blah blah blah, and so on and so forth. So we move on. This one you get about 4 marks. So you shouldn't waste too much time on this question. Now we go to this question. It's a state in terms of their structure, why metals are good conductors. In terms of their structure, why metals are good conductors of electricity. Why? Because it's just 1 mark. Because metals are good conductors of electricity because they have a free mobile electrons. So question 7. Question 7 is a state why metals are good conductors. Because they have free mobile electrons. They have free mobile electrons, or what you call delocalized electrons. Okay? Someone else might write that. Free mobile electrons. Because metals, they have free mobile electrons, so they're good conductor of electricity. They're good conductor of heat and electricity. They have free mobile electrons. So once you mention this, you get your 1 mark. You don't need to waste time because in Cambridge exam, there are so many questions. You don't need to waste time on anything, right? And move on. Especially for 1 mark question, do not waste a lot of time on it and move on. So because you need speed and accuracy in order to be successful or to have good grades in the exams. Okay, now we move to the next question. It says a cylindrical metal wire W1 of length L, okay, and a cross-sectional area A has a resistance of 60 ohms. Has a resistance of 60 ohms. Now, a second cylindrical wire W2 has length L, meaning the length is now halved. And the cross-sectional, once the length is halved, the cross-sectional area will double. And is made of same metal. Determine the resistance of W2. So the first thing we do is we identify W1. Here we are going to do the resistance of wire. So W1 has a length, we can choose a certain length, has a length L1. Has a length L1, and we can choose L1 with certain length. We can assume any certain length for L1. Okay, the wire has this length L1. So if this is the length of the wire L1, then the area is A or A1. The area is A1, so it has area A1. Now W2, another wire 2, W means wire in this regard. Wire 2, say the length is half. So because it's L1 over 2. So the length has been halved. When your length is halved in the rules of resistance, then your cross-sectional area will double. So area will be 2A, meaning it will be shorter and with a thicker surface like this. Half of the length, like this. This is wire 2. So the area is 2A. And the length is L over 2. So now the resistance of this wire 1, R1, is 60 ohms. Resistance is 60 ohms. Now find the resistance of wire 2. Okay, find the resistance of wire 2. So to find the resistance R2, R2 will be equal to R1 times half of the length of R2 okay, so times one all over the area. So this one will give us 16 times 1 all over 4. Because 1 over 2 times 1 over 2 is 1 over 4. So this will give us 4. This will give us 4. So R2 will be 4 ohms. R2 will be 4 ohms. Okay, so our R2 will be 4 ohms. Okay, so that's that for this question. Now let's move to, you get 2 marks for this calculation. Now the effective resistance of W1 and W2 when connected in parallel. Now I say we should calculate the resistance of W1 and W2 when they're connected in parallel. You know, in parallel, if there are 2 resistance, you can do product over sum. You know, 1 all over W total, okay, is R anyway. Okay, if you don't want to be confused, I can use R. If you don't want to be confused, I can use R. 1 over R total is equal to 1 all over R1 plus 1 all over R2. This is the formula for parallel connection. Okay, when resistances are connected in parallel, this is how we find their effective resistance. Effective resistance means the total resistance. When they use the word effective, they're talking about the total resistance. Okay, so this is the formula for calculating the effective resistance or the total resistance. So this question 7B, right? 7B Roman figure 2. Okay, 7B Roman figure 2. So this is 7B Roman figure 2. The first one we did was 7B Roman figure 1. This one was 7B Roman figure 1. Question 7. Okay. So, but we can, there's a shorter way without saying 1 all over 16 because W1 is 16 or R1 is 16. In this case, I'm equating W to be equal to R, to be R. Okay? Just for usability and for familiarity. Because many of us are familiar with using R for resistance. So we say equal to R. So you can say 1 over 60 plus 1 over 4 and then you can finish it up. You're going to get the same answer. But there's a shorter way. R total, straight away R total is equal to the product over the sum. Product over sum is equal to product over sum. So product meaning their multiplication of the 2 resistances over the addition of the 2 resistances. That's the meaning. So the parallel connections of resistance can be resolved, or total resistance in a parallel connection can be resolved by simply saying the product of resistances over the sum. Okay, so the product is 16 times 4, 16 multiplied by 4. Remember, R1 is 16 and R2 we calculated is 4. So you see the answers, if you fail the first one, you will fail the second one definitely. So that's why you have to be careful when you solve the problem, because they are interconnected. We are using the resistance we calculated in the 7B Roman figure 1 to solve here. So if you couldn't do that, it therefore means you cannot do this. So you see, it becomes a cumulative failure. So we just multiply and then we add. We say 16. At the bottom we say 16 plus 4. So 16 times 4 is equal to what? R total, which is 60 times 4. Is this 64? 60 times 4. 64. So we say 64 divided by 20. 64 divided by 20. We'll get 3.2. We'll get 3.2 ohms. This is the equivalent resistance. This is the equivalent or the total resistance. When these 16 and 4 are connected in parallel, the total resistance they offer to the circuit is just 3 ohms, 3.2 ohms. That's the total resistance they offer to the circuit. Okay? When they are connected in parallel, so meaning if I want more current, it's better to connect my resistance in parallel. If I want more current to flow in the circuit, because resistance they oppose the flow of current. They oppose the flow of current. Resistance, they oppose the flow of current. So if you want more current, better you connect your resistance in series, because in parallel. Because why you have to connect in parallel if you want more current? Because the overall resistance they offer, you see, 60 and 4. If it was in series, the resistance would have been 20. It would have been 60 plus 4, 20. But in parallel, they are only offering 3.2 ohms resistance. They are only offering 3.2 ohms resistance. Is that okay? So that's that for them. Let's move on quickly to the C of these questions. Okay? He said the parallel pairs of resistors in B Roman figure 2 is connected to a battery that is made from 3 cells in series. A battery that is made of 3 cells in series, each of electromotive force EMF E. Now, there is a current in each resistor. State the EMF of the battery. Okay, they just want us to state the EMF. They're not looking for us to do much. Is that okay? But normally, this circuit, this parallel connection, the parallel connection means that I'll draw my resistor R1 like this, and I'll draw my resistor R2 like this. Okay, I will bring them to a common point. Okay, I'll bring that to a common point. So here is a junction where the current splits to both of these. I'll bring them here. Okay. From here, I can go to my cell. I can go to my cell or battery. Okay. The battery is made up of 3 cells. 1, 2, 3. So this battery is made up of 3 cells. So this battery is like this. If you like, you can add ammeter, switch, and whatever you want to add. But this is the basic circuit. This is your R1. This is your resistor R1. And this is your resistor R2. This is your resistor R2. Okay, this is your battery. And then each of them is made up of EMF E. Each of these cells is made up of EMF E. So if you want the total EMF here, it will be 3E. Okay, since they designate the value for E, for the EMF. Now it says, say the EMF of the battery. So the EMF of the battery will be 3 times E, because each one is E. So Roman figure 1, don't know if it's Roman figure 1 or so, or thereabout. So see Roman figure 1, it will be E 3 times E, because each cell has EMF E. Okay, so the total EMF will be 3E. If they give us the value, then sometimes E could be 1.5 volts. But this question did not give us the value of the electromotive force. So you just write 3E. Okay, you write the answer in terms of E. Is that okay? So that's that for that. We move on to the next question. See Roman figure 2, we say the current in the battery is IB. The current in the battery, the battery has the highest current, so it's IB. And this current is the one that flows to resistor R1 and resistor R2. Is this one that flows to, this current flows, when it gets here, it splits. When it gets to the junction, it splits. This current flows through like this. Okay, it flows like this. And then when this current gets to this junction, it splits. Some go here and some go here. Okay, this one has a bigger ohms, 16 ohms resistor. And this one has a smaller ohm resistor, R1. So more current will be here. The current, the bigger the resistor, the smaller the current. So this I2, if here is I2, then here we have bigger current than I1. I1 is the one that is on arrow 1, that is flowing on arrow 1. So I2 will be bigger. The current in I2 will be bigger than the current in I1. Because the bigger the resistance reduces the value of current. So if your resistance is big, your current is small. If your resistance is big, your current is small. So what we have in C Roman figure 2, question 7 C Roman figure 2, is that IB is the current in the battery, which is the biggest of them all. In fact, that's the source, is bigger than I2, which has 4 ohms resistor, and I2 is bigger than I1, which has 60 ohms resistor, resistor. So in the question, we're going to look for an option, because it says we should place a tick in one box to indicate how these 3 currents are related. So you look at this, or this one, anyone that did not start with IB is wrong. So the first 4, 1, 2, 3, 4, they are all wrong. No need to consider them. You only consider the 2 that start with IB. You try and see which one is correct. So you can see IB is bigger than I1. No, this is not the right arrangement. IB is bigger than I2, and I2 is bigger than I1. So this is the correct arrangement. So we tick this box. In the exam, we just tick this box. That's it. They just want us to tick it, just one mark. Okay, which is this. IB is bigger than I2, I2 is bigger than I1. So we tick that box that connotes that. And we get the 7 marks for this question. Now let's move to question number 8. Question number 8 says in a laboratory, it says in a laboratory at normal room temperature, 200 grams of water is poured into a beaker. 200 grams. So we begin to give the parameters, okay, so that we can work from the known to the unknown. We can work from the known, from what is given to what is not given, what they want you to find. The mass is 200 grams, mass of water. So I write MW. Mass of water is 200 equal to 200 grams. Mass of water is 200 grams. Okay, and let's see what the question still has to tell us. Say the mass of in the laboratory at normal room temperature, the 200 grams of water is poured into a beaker. So we pour 200 grams of water into a beaker. A thermometer placed in the water has a reading of 22. Okay, thermometer placed. This is like change in temperature. Okay, because they're not bothering giving you initial temperature and final temperature. So this change in temperature is simply equal to 22 degrees Celsius. They're giving us a change in temperature as 22 degrees Celsius. And let's see what which other parameter the question has for us. Is a small piece of ice at 0 degrees Celsius are added to the water one by one. Now the mixture is stirred after each addition until the ice has melted. Now this process is continuous till the temperature recorded by the thermometer is 0 degrees Celsius. So they are adding ice step by step, one after the other, and they keep stirring the mixture until the ice has melted, and then we see what happens after that. Now the total mass of ice added to the water is found to be 60 grams. Mass of ice. So mass I, right, MI. Mass of the ice is equal to 60 grams. Is equal to 60 grams. Is equal to 60 grams. Now let's take a look at what the next day. The specific capacity of water is 4.2 joule per gram per degree Celsius. So we don't need to convert the mass. If this was in the joule per kilogram per degree Celsius, we have to convert this mass to kilogram by dividing with 1000. But this one is already in joule per gram, not joule per kilogram. So we leave the mass as gram. Okay, so let's write the specific capacity of water. We write the specific heat capacity C. In most cases, most books they write C, but I write CX. Specific capacity of water is 4.2 joule per gram per degree Celsius. 4.2. If it's kilogram, it's 4,200 joule per kilogram per degree Celsius. If it's a gram, it's joule per gram. Joule per gram per degree Celsius. Is that okay? So this is what we have. This is the specific capacity of water. Let's see what the question wants us to find. Now the question wants us to calculate the thermal energy lost by the water originally in the beaker. The water originally, before you add the ice. Listen to the question. The water originally. Okay, calculate the thermal energy lost by the water. They did say calculate the thermal energy lost by the water and the ice. If they have said that, we would have added the mass of the ice. Okay? So make here, or you calculate from water only, you calculate for ice only, and then you add them together. But this question is different. Say, calculate the thermal energy lost by the water in the beaker, lost by the water originally in the beaker. So the thermal energy, let's you know the formula for calculating heat energy, thermal energy. Some books, some texts, they use Q for this thermal energy, some use E. So in this case, let's quickly use E for convenience. We say E equal to the mass multiplied by specific heat capacity. Specific heat capacity, I say C subscript S. Then times change in temperature, delta. This delta means change in temperature, delta T. Okay, so this is the formula. Now this is the thermal energy that is lost, we are calculating. So we say this is equal to, this will be equal to the mass of water is 200. The mass of water is 200 multiplied by specific capacity of water, which is 4.2. Specific capacity of water, which is 4.2, multiplied by the change in temperature, which is 22. What do we get? 200 times 4.2 times 22. So we get 80,400 joules. 80,400 joules. In the exam, they might round up to the nearest 1,000. They love doing that, okay, in physics paper. If they do that, they see the same thing, okay, 80,400 or 80,400 joules. Okay, so that's the energy we have calculated. And let's see the next question. This one we calculated, we got it 2 marks. The next question says, assume that all the thermal energy lost by the water originally in the beaker is transferred to the ice. All the energy lost by the water in the beaker is transferred to the ice. Calculate the specific latent heat of fusion. Calculate the specific latent heat of fusion of ice. Okay, so to calculate specific latent heat of fusion, we always say either you write E. Okay, let's use E. Since we stick with E, let's stick with E. Specific latent heat of fusion, the energy is equal to M, the mass multiplied by the latent heat of fusion, LF. This F is a small subscript. Okay, LF. So this is what they ask us to calculate. So we're going to make it the subject of formula. So make LF the subject. LF is one parameter, okay? They are not 2 parameters. So LF, specific latent heat of fusion, is equal to the energy divided by, assuming all the energy lost here is transferred to the ice. So we say this energy that is lost, 80,400, divided by the mass of the ice. Divided by the mass of the ice. This case, not the mass of water, the mass of the ice, because we are calculating the specific latent heat of, specific latent fusion of ice. We are calculating the specific latent heat of fusion of ice. Okay, so this is the formula we're going to use now, and which means our LF, the specific latent heat of fusion, the specific latent heat of fusion is equal to the energy we've calculated, the energy that was lost, the energy lost by the water originally for 80,400. 80,400 divided by, sorry, this zero does not exist. 80,400 divided by okay, 80,400 divided by the mass of the ice, which is 60 grams. 60. If you don't know unit, if you don't know the end unit of latent diffusion, be putting the unit as you are doing. Mass is in gram, so you now know that your final answer is joule per gram. Joule per gram. So if 0 cancels 0, what do you get? So if you divide this, what do you get? 80,000. Huh? So we get our LF to be equal to 308. 308. In the exam, they might round up to the nearest 10, and they might write 310. Okay? They might write 310. It's the same thing. So 308 joule per, because physics is a law of approximating to the, you must write units. If you don't write units, 308 what? Is it 308 apples? If you don't write units, it's not considered correct in physics. You will not go to get your full marks, or rather you lose even almost all the marks. Now let's move on, and these are another 2 marks which you have gathered. Suggest a reason for any inaccuracy in the value of the specific latent heat of fusion of ice calculated in B. Assume the temperature reading in the values for the mass of the water and the mass of the ice are accurate. What could be our reason for the temperature? Okay, the reason for the inaccuracy could be the loss of the heat supplied to the surrounding. Okay, just 1 mark. The loss of the heat that is supplied to the surrounding. Loss of heat. Okay, to the surrounding. Loss of heat, or loss of thermal energy. Thermal energy. Loss of thermal energy to the surrounding. Okay, so this could be the being of the word. Now let's see. We've done the first part. Let's see if we still have for this question. How many? 1, question 9. Okay, so we will stop here today, and we will do the last 3 questions for part 3 of this video. So thank you for joining us.